this computer. Okay. Thank you very much. So.
Okay. Thank you very much, Maria. Today I'm going to talk about a specific theoretical problem that has been bothering me for some time, but was actually identified in the original paper, which was published by Coates back in the 70s, but not actually solved. And the problem that I'm going to talk about involves diffusion theory and applies to transformations that are reconstructive in nature. So, for example, the formation of allotromorphic ferrite, which is illustrated on the left, and the pearlite, which is illustrated on the right. And you can find more details about this on my website as usual. So this is the original paper on diffusion, or rather on Fick's law of diffusion. And you know, Fick was actually in the Department of Anatomy and was looking at diffusion in liquids, the diffusion between salty water and water. And he came up with the idea, you know, which was also there in the diffusion of heat by Fourier, for example, where he put the flux of diffusion to be proportional to the concentration gradient. Okay, so this is the concentration gradient here, and this is the diffusion flux. Flux means the amount of material flowing through a unit area in unit time. And the proportionality constant here is the diffusion coefficient, and the minus sign arises because, you know, the flux is going in the positive z direction, but the gradient is negative. So this is the classic Fick's law of diffusion. And I want you to note very carefully that this is a constant. It doesn't depend on the magnitude of the gradient here. Okay, so it's a proportionality constant, and the effect of the gradient simply comes in through this term. Now, we know since those days that Fick's law is not correct in the following respect. You know, if you observe ice floating in seawater, then the ice is pretty pure, whereas the ocean contains a larger concentration of salt. And no matter how long you observe the ice and the water, there will be no tendency for the salt to diffuse into the ice, even though the concentrations are very different in both the ice and in the water. So clearly, it's not obeying Fick's law, in the sense that we have a concentration gradient, and yet, you know, no change in composition, no matter how long I observe this system. And the reason we now know is that the diffusion flux depends not on the concentration gradient, but on the chemical potential gradient. Now, I know that these lectures are meant for a very wide audience, so I'm going to explain the meaning of chemical potential in the best way that I can. So imagine that we have a phase, a single phase, and it consists of two components, A and B, and this is the free energy of pure A and the free energy of pure B. And then we make a solution of a particular composition X, and that will have a certain free energy G, which is a function of X, because if I take another solution here, it will have a different free energy. Now, if I draw a tangent to this curve, then I can write this equation that the free energy G of X is simply a linear combination of the free energies of A and B weighted by their concentrations. So effectively, what this equation says is that we have separated out the free energy of a solution into two parts. One is purely due to the A atoms, this term here, because this is the concentration of A and the chemical potential of A. And this is the concentration of B and the chemical potential of B. So you need to think about chemical potential as giving you an indication of the free energy of B atoms in a solution of a particular composition. Of course, if I alter the composition, then the position of that tangent will also change, and therefore the chemical potential will alter. So it's a function of chemical composition, but it really identifies the contribution of B atoms and A atoms to the total free energy of a solution. So it follows that, when I put ice and water containing salt into contact, and I draw a tangent which is common to both of those, then the chemical potential of water in seawater and water in ice will be exactly the same, because we are sharing a common tangent between the two phases. And the same applies with respect to the chemical potential of sodium chloride in seawater and sodium chloride in ice. So the reason why, no matter how long we observe this system, there won't be any tendency for salt to diffuse into the ice is simply that the free energies of the sodium chloride molecules in seawater is exactly the same as the free energy of the sodium chloride in ice, even though the concentrations are different. Okay, so the concentrations in equilibrium are clearly different, and yet there is no tendency for diffusion because these conditions are satisfied. So if we go on to look at this for the iron manganese system, say, and we have a free energy curve like this, and there are two regions in that solution with different concentrations, then there clearly will be a driving force, which is the difference in chemical potential between those two regions, to induce diffusion. And it's only when these two potentials and these two potentials become equal that diffusion will stop. Okay. Now, notice in this case that the chemical potential increases as I increase the concentration. Okay. So we write that the change in the chemical potential with the concentration is greater than 0. Okay. So we have a positive value of d mu by dc, how the potential changes with concentration. But you will know from your undergraduate lectures that we can also have a curve which is of this shape, where when I increase the concentration from x1 to x2, the chemical potential actually decreases. And this is a little bit bizarre. It means that this is less than 0. And it means that if I take a solution between these 2 points, if I take a solution of that composition, it will tend to separate out into a solute-rich and a solute-poor region, spontaneously separate out. In other words, there's a driving force for separation. And this kind of a solution we associate with atoms that like to be next to their own kind. All right, so the manganese atoms prefer to be next to manganese atoms, and the iron atoms prefer to be next to iron atoms. Of course, this represents what we call the Spinodal decomposition, where you start off with a completely homogeneous solution here. And nevertheless, if there is sufficient thermal activation, then there will be a tendency to develop solute-poor and solute-rich regions. In other words, diffusion is happening against a concentration gradient, all right? So it's uphill diffusion. But it's perfectly natural because there is a reduction in free energy. Okay, so going back to Fick's law, we had the equation that the flux is proportional to the concentration gradient, and D is our diffusion coefficient, which is independent of the magnitude of the gradient. We need to express that differently in terms of the chemical potential gradient. So because mu is a molar quantity, we also multiply it by the concentration here. And this is another proportionality constant, which we call mobility of atoms. So if I now compare these two equations, so here the flux is written in terms of a free energy gradient, here the flux is written in terms of a concentration gradient. So if I now compare these two equations, but before I do that comparison, I need to expand this term into a component due to how the potential varies with concentration, and this is our concentration gradient. So this term is identical in these two equations, and therefore we get that the diffusion coefficient is actually a function of how d mu varies with, how chemical potential varies with concentration. And that is the reason why when du mu by dc is negative, we get uphill diffusion. But I emphasize again that d here is independent of the gradient. Okay, so both of these equations have a number d which is independent of the magnitude of the gradient or any function of the gradient. Okay, let me now treat the growth of ferrite in a binary iron carbon system just to establish some basic principles. Okay, so here is a one-dimensional thickening of ferrite. That means I'm looking at the thickening of a layer of ferrite at a boundary, and we assume local equilibrium. That means we assume that when the phases are in contact, the compositions of both of the phases at the point of contact is given by a tie line of the phase diagram. A tie line is simply where the chemical potentials are identical, even though the concentrations are different, just like in the ice water example that I gave you. And C bar here is the average concentration. And I'm also going to assume that we are looking at the stage of transformation where there is no enrichment of the austenite far from the interface. So no change in C bar away from the, far enough from the interface. So when the ferrite starts growing, we develop a profile of concentration at the alpha gamma interface. And I'm just using a straight line here. This is called the Zener linearized approximation. This would in reality be an error function, but doesn't change what I'm going to say. So we have a diffusion distance delta z here, and z star represents the position of this interface. And because of local equilibrium, the compositions of the two phases at the interface are in equilibrium. Okay. Right, now let's see when we get what happens when we get a small increment in the thickness of the ferrite. So we change from this black profile into this red profile, and in the process, that much solute has to be pushed ahead of the interface. So the rate at which solute is partitioned between the two phases is given by this concentration minus this concentration times the rate at which the interface is moving. Okay, so in any diffusion theory, you'll get a term like this, which is the rate of solute partitioned, the difference in concentrations at the interface multiplied by the increment in the thickness of the ferrite divided by the corresponding time increment. So this is the rate at which solute is partitioned. And if we want to maintain equilibrium at the interface, then that solute must be carried away from the interface by diffusion. So we have a second term here, which is the flux down the interface, which is minus the diffusion coefficient times the gradient in concentration. And of course, if we are going to maintain these concentrations fixed, then these two terms must balance here, okay? That the rate of solute partitioned must equal the diffusion flux away from the interface. And because we are using the straight line approximation, this term is given by this. And I can solve for delta z here by mass balance, because this area in this badly drawn diagram must be equal to this area. Okay, so it's easy to solve for delta z. And when you substitute this mass balance term for delta z, you get that the thickness of the ferrite will vary with the square root of the diffusion coefficient multiplied by the square root of time. In other words, parabolic thickening. And the reason why you get this parabolic curve, the shape, is that as the ferrite grows, the gradient here will become more and more gentle as a greater amount of carbon is partitioned into the austenite. So straightforward, this is parabolic thickening assuming diffusion-controlled growth. How can we generalize this now to a ternary system where we have, in addition to carbon as a solute, we also have manganese, say, or any other substitutional solute? Well, we have to deal with a ternary phase diagram here, and this is at a constant temperature. So instead of free energy curves, these are now surfaces in 3 dimensions, okay? So imagine the bottom half of football. So this is the free energy surface of ferrite and the free energy surface of austenite. And instead of a common tangent, we have a tangent plane here, which touches both of those surfaces. So imagine 2 footballs and you touch a plane to both of those footballs. There will be contact points, which when you join will give you a tie line where the 2 phases are in equilibrium, even though their compositions are different. But of course, we have an extra degree of freedom here. We can take that tangent plane and still keep it in contact with the 2 footballs and rock the tangent plane. In other words, there's an infinite set of tie lines that I can generate by rocking this tangent plane while still maintaining contact with these surfaces. So at a constant temperature, I can get this 2-phase field, which is the field of tie lines generated by rocking that tangent plane. In the binary system, we just had 1 tie line, but here there's an infinite number of tie lines within the alpha plus gamma phase field, where the conditions for equilibrium, i.e. the quality of chemical potentials of all the phases, would be satisfied, and therefore that is an isothermal section, for example, of the iron manganese carbon phase diagram, where you see a myriad of tie lines here. And of course, all the wonderful work that has been done in the past, producing things like calfat, thermocalc, empty data, fact stage, and so on, allow you to calculate these tie lines for most of the systems that we are interested in. And if there are others which we do not have access to, then presumably some sort of work can be done to generate the thermodynamic data necessary. So the important point is that we know the tie lines, all right? So take that as a given. I'm not going to go into the calculation of tie lines. It's reasonable to assume that we have access to tie lines, okay? So going back to this equation for the binary system where we balanced the rate of solute partitioning against the diffusion flux away from the interface. Of course, we now have 2 solutes, the manganese and the carbon. So we have a pair of equations for balancing at the interface. This is the rate at which carbon is partitioned, and this is the rate at which it's taken away from the interface in order to maintain local equilibrium. And similarly, this is the rate at which manganese has to be pushed ahead of the interface, and this is the rate at which it must be carried away. And the classic problem here is that these 2 equations must be satisfied simultaneously. Okay, there is only one interface, and that the diffusion coefficient of carbon is many orders of magnitude bigger than the diffusion coefficient of manganese. So how can these 2 equations be satisfied simultaneously when these terms are not all that different? Okay, they are different, but they are not different by the many orders of magnitude here. So typically this might be 6 to 8 orders of magnitude difference in diffusion coefficient. So there are 2 ways in which you can satisfy these 2 equations simultaneously. because we have this extra degree of freedom that we can select the tie line which will allow us to satisfy these equations. There isn't just a unique tie line in a ternary system. So one way is that we choose a tie line that minimizes the concentration gradient of carbon to compensate for the very large diffusion coefficient. And that will lead to the long-range partitioning of manganese between ferrite and austenite. And that is not the case I'm interested in today. I'm interested in the transformation happening at large supersaturations. And at large supersaturations, the only way to satisfy these two tie line equations simultaneously is to select a tie line which maximizes the gradient of manganese. Okay, so if I maximize the gradient of manganese, then I compensate effectively for the low diffusion coefficient of manganese, and then the flux of carbon and manganese can keep pace. So just to illustrate that diagrammatically, this is our ternary phase diagrams, and there's a couple of tie lines, but actually this field consists of an infinite number of tie lines. And let's say that this is our alloy of interest, and we've quenched it from a high temperature into this temperature, and it is at a high supersaturation because it's closer to the ferrite phase field than to the austenite. If I'd chosen an alloy here, it would be a low supersaturation. What I want to do is to select a tie line that will maximize the gradient of manganese. That means I want very little manganese to be partitioned. So if I draw a construction line here, which makes the ferrite have a manganese concentration that is almost identical to the alloy, then very little manganese is partitioned, and the concentration spike of manganese at the interface becomes extremely sharp because very little manganese. The composition of the ferrite is almost identical to that of C bar, the average concentration in the alloy. And of course, the carbon will partition as usual. So by choosing that tie line, you allow the fluxes of manganese and carbon to keep pace with each other as the interface moves. And this is sort of incorporated in many pieces of software which are now routine in most material science departments and industry. For example, Dictra and MatCalc and so on. So it's very easy to do these calculations even for a multi-component, more than 3 elements. The trouble is, and this is the major problem, okay? The trouble is that if you calculate this distance here, that means the diffusion distance delta Z, which I illustrated earlier, it's ridiculously small, okay? When you have this negligible partitioning local equilibrium mode, the diffusion distance is unphysical. Okay? There's no possibility of defining a concentration spike at the interface, which is that small. And of course, this was identified by Coates himself. He says it is conceivable that at very high growth rate, that means large supersaturations, the diffusion zone becomes so thin as to exist only mathematically. Right? So he didn't actually propose a solution to this. So how do we actually proceed? Well, luckily, we can resort to the theory of spinodal decomposition, where I explain that if you have a free energy curve with a shape like this, so that the change in chemical potential with concentration is negative, then it will tend to spontaneously decompose into solute-rich, solute-poor and solute-rich regions. And this movie here illustrates a computer simulation of the iron-chromium system, where you get this spontaneous separation into chromium-rich and chromium-poor regions. And the same sort of thing happened in the universe. when after the Big Bang, matter started to cluster. Okay, so for about 100 million years, there wasn't sufficient clustering of matter to create stars. So there was no light at all in the universe, and that constituted the original dark ages, if you like. Okay. Now, the process being illustrated here and here is that, look, supposing I start off with a completely uniform composition, then because of the way in which the potential changes with concentration, you will spontaneously get composition waves. Okay? And those waves will increase in magnitude with time until eventually equilibrium is reached. The problem with ordinary diffusion theory, which was identified by Hilliard and Kahn and Hilliard, is that if you treat your composition wave as a series of Fourier components, then the wave with the smallest wavelength will grow most rapidly. And that leads you to the bizarre scenario that in a system where atoms want to cluster, you will actually get ordering, because the smallest wavelength is, of course, the interatomic spacing. So that cannot be correct. Okay? That simply cannot be correct. And that comes about because the diffusion coefficient is actually a function of the concentration gradient.
Heeft het iets te maken met de installatie van Zoom of zo?
Somebody needs to mute themselves, okay? So the diffusion coefficient actually becomes a function of the concentration gradient. Well, it is a function of the concentration gradient, but it isn't there in either the Fick's law or in the modified Fick's law, where we look at chemical potential gradients. And the outcome of this, I will show you, is that large gradients actually retard diffusion. So that goes completely against your intuition. But if I have a wave with a very small wavelength, then that will retard diffusion. And the origin of that is that the free energy is actually a function of the gradient of the concentration as well as of the average concentration. So if I show you what Hilliard did in his review on spinodal decomposition in one of the classic phase transformation books in our subject, he expressed the free energy of a solution, of a heterogeneous solution, as a function of the gradient. So A here is the gradient of concentration, and of the second derivative of the gradient of concentration, and expanded did this polynomial expansion in terms of these two variables. So this is the free energy per atom if you have a homogeneous solution with a concentration C bar. And these are the terms which arise because of the gradient itself, and this is because of the second derivative of the gradient. So when we look at a heterogeneous solution, the average free energy that you would get if the solution was homogeneous is different from that for a heterogeneous solution. So if I substitute for A and B in these terms and do a lot of algebra, then you end up with an equation like this, where this is assuming that the solution is completely homogeneous. This is a term which depends on the gradient, on the second derivative of the gradient, and on the square of the gradient. Now, this term cannot exist because, the free energy for a centrosymmetric system, the free energy cannot depend on the sign of the gradient, right? So you can eliminate this term, and we end up with just three terms in there: the homogeneous solution, the second derivative of the gradient, and the square of the gradient. And we are integrating now with the volume of the material. And again, if you do a significant amount of algebra, you end up with this classic equation, which gives you the free energy of a heterogeneous solution is a function of the average of the free energy of a homogeneous solution. Notice this term has disappeared again because we have a gradient here, and free energy can't depend on the gradient, sign of the gradient. So we end up with just terms in the gradient squared, okay? And this is called, this is the volume per atom, and kappa is called the gradient energy coefficient, okay? So this is the additional term which must be taken into account when we are dealing with all gradients, but it's only important if we are dealing with very steep gradients, as you will see when I put in some numbers. This equation is also, of course, the basis of phase field theory. But the problem with phase field theory is that we can't actually define a good enough interface for what we need in terms of negligible partitioning local equilibrium. So I'm going to show you some numbers now on how significant this is in the context of the negligible partitioning local equilibrium model. So I did some calculations for the iron chrome system, and here we have the contribution from the gradient energy term. It's positive. That means it will oppose the diffusion process, and that's why large wavelengths in Spinodal decomposition actually happen, whereas small wavelengths do not. Now notice that even at 0.1 nanometer diffusion distance, we have a huge cost in terms of free energy. Okay, so remember that in the case of the austenite to ferrite transformation, the driving force for transformation can be of this order. So if I go to 0.01 nanometer, which is like the numbers I illustrated earlier from the publications that I referenced, that cost would be overwhelming. Okay, so there is no possibility of getting negligible partitioning local equilibrium if the gradients are that steep. It's just not possible. There would be no driving force left for diffusion. So let's just look at experimental evidence for the NPLE method. And I claim that NPLE has never been observed experimentally in kinetic data, where you measure the thickening rate of allotriomorphs as a function of time. And one of the most important reasons is that the real structure of an allotriomorph is far more complicated than one-dimensional or two-dimensional thickening, etc. So we have, the classic prediction that Smith made of curved interface here and a faceted interface. And if I blow this up, there's a ledge mechanism and so on. So the comparison between growth data on allotriomorphs and theory is fraught with difficulties, all right? Because the structure of the interface and the topology of the interface are simply not taken into account. Now, there's an awful lot of theory on how ledges would move under diffusion control, but there is only one paper ever published, and that is not a full theoretical outcome on the prediction of the ledge heights, for example. So there is no way of predicting the topology of the interface. In other words, the step height and the step spacing. Okay, so resorting to kinetic data and claiming NPLE is simply not reasonable. Perlite always shows partitioning. Okay, there is never a case where you have obtained perlite without the partitioning of solute. So this is classic work by Ridley and Chance, where we are plotting the chromium partitioning coefficient as a function of transformation temperature. In all cases, there is partitioning, and furthermore, the partitioning is quite different from what you would expect from local equilibrium. That's not the case for displacive transformations, where you can definitely get no partitioning, but by a different mechanism. Okay, so there's never been a case of perlite where you don't have the partitioning of substitutional solutes. Okay, people sometimes use the NPLE curve, which you can easily calculate using the commercial software, and check to see whether the bainite reaction stops there. But that makes no sense at all, because NPLE is just a transient condition. If it exists, it's a transient. Because as the ferrite or whatever is growing becomes bigger, the tie lines will shift towards partitioning local equilibrium. Okay, so this is not a limiting condition. And you should never use it as a limiting condition, because you will get what's known as tie line shifting. Now, there are plenty of warnings in the theory of irreversible thermodynamics, which is what we use to justify the assumption of local equilibrium, that the situation must not be too far removed from equilibrium. In other words, when we are transforming at high supersaturations, you cannot assume that you will get local equilibrium. And there are many, many papers on this, but this is a beautiful description here in Jack Christian's Theory of Transformations in Metals and Alloys on page 98. Okay, atom probe. You would have thought that with the atom probe, you can solve all the problems, because Baptiste, Professor Baptiste, I think his name is, the second name is Giraud, right? Baptiste Giraud. He gave a talk on...
Baptiste Claude.
Yeah, that's it. Thank you. Yeah. So he gave a really nice talk on the atom probe, which I've watched repeatedly myself to understand. Okay, and he specifically addressed spatial resolution, and he demonstrated the enormous amount of care that is necessary in the interpretation of data to actually get reasonable spatial resolution as opposed to chemical resolution. And I think his talk was nevertheless optimistic, okay, which is good, because he can do better. He is an expert on the atom probe. But look at this concentration profile, for example, which was published in one of the Nature journals. It makes no sense at all, okay? So this is identified as the position of the interface. The compositions of the two phases at the interface are exactly identical, which goes against, chemical potential being the governing criterion. And you have these gradients in both the phases. It makes no sense whatsoever, okay? The width of this is many, many nanometers. So I think there is a real problem of spatial resolution. And here's another example where, it's claimed that this is negligible partitioning local equilibrium without actually comparing the detail against theory. And this is identified as the position of the interface. And it makes no sense to have a hill of concentration inside one of the phases, okay? So I think there is a real problem with, if you like, the routine use of the atom probe. You need someone like Baptiste to go into great depth to see how we can look at these profiles very, very carefully and with detailed interpretation at interfaces between austenite and ferrite. So there are no atom probe data that I know of. And, there was a review some years ago by Purdy and others in ACTA, I think associated with the Alemi meetings, where they reviewed a large amount of data. And I could not see in any of those data. So there are 25 pages of review of experimental data, and I could not find anything to justify NPLE. Okay, just to give you an idea of how we can implement this in software. So I have only done my calculations by by calculator, but hopefully somebody can implement this in the commercial software so that we don't get into the trap of treating very steep concentration gradients carelessly. So if you have diffusion-controlled growth and the compositions at the interface are given by a tie line here, then all of this free energy is dissipated in diffusion here. Okay. Now, of course, there will be other processes like interface and so on, but let's not worry about that at the moment. So if I have to account for the cost of a steep gradient, then this free energy curve would actually increase, okay? And the concentration x gamma alpha would move towards x bar, and therefore this gradient would automatically become gentle. In other words, we would not get NPLE partitioning. So when I do the calculation by hand, what it means is that I can only do a certain number of cases. But if you implemented it into some computer software, then this could be an iterative process to see how you start off the growth and how it develops into the level of partitioning. Now, you can also treat non-equilibrium partitioning, but I think this is enough for today. And I spoke about this problem in this article here. And this is the article which I referred to for ledge nucleation, which is really an unsolved problem, okay? If you want to work out the topology of the alpha-gamma interface, it's simply not possible. And I've also discussed this in more detail in this book, which Maria mentioned. So I'll be very happy to engage in discussion. Thank you. Shall I stop sharing the screen?
Yeah, you can start here. Yes. Thank you very much for the very interesting presentation. So yes, the presentation is open for discussion.